Hello and welcome to the Hydrogen Engineering Masterclass. Before we start discussing fuel cell, hydrogen storage tank, electrolyzer, or hydrogen powered vehicle, it is important to understand one fundamental idea. Hydrogen is not just a gas. Hydrogen is an engineering ecosystem. When most people hear the word hydrogen, they immediately think about a fuel for a car or replacement for a petrol and diesel. However, the reality is much larger than that. Hydrogen connect renewable energy, chemical engineering, material science, thermodynamic, electrical engineering, transportation, and industrial manufacturing into the one integrated system. In this course, we will study not only the science behind the hydrogen, but also the real engineering challenges that determine whether a hydrogen project succeeds or fails. We learn how hydrogen is produced, purified, compressed, stored, transported, and finally converted into the useful energy. Most importantly, you will learn to think like an engineer. Instead of asking whether hydrogen is good or bad, you will learn to ask right questions. Where does hydrogen come from? How much energy was required to produce it? How efficiently can it be stored? What are the losses? What are the safety concerns? And where does hydrogen actually make sense compared to the batteries or conventional fuels? By the end of this course, you will have a complete understanding of the global hydrogen value chain and engineering realities behind it. Let's begin. Slide conception about hydrogen is that an energy source. Technically speaking, hydrogen is not a primary energy source. Hydrogen is an energy carrier. Let's understand this with a simple example. Coal contains energy naturally. Natural gas contains energy naturally. Crude contains energy naturally. These are the primary energy sources because we can extract them and use them directly. Hydrogen is a little different. Hydrogen does not exist freely in a large quantities on Earth. Hydrogen is usually bound to other elements. For example, in water, hydrogen is chemically bounded to the oxygen. In natural gases, to the carbon. Hydrogen, we must first spend energy to separate it from these compounds. That means hydrogen is more likely a rechargeable battery than a fuel source. We put energy into hydrogen during a production. Later, we recover that energy during use. This ability to store and transport energy is exactly why hydrogen is becoming important in the energy transition. Today, global hydrogen demand exceeds 100 million tons annually, mainly for the industrial applications such as refining and fertilizer production. However, producing hydrogen with low emission remains one of the major engineering challenges of our times. Slide 3. Hydrogen project is never a single machine. This is the one of the most important lesson in hydrogen engineering. When people see a fuel cell vehicle, they often focus only on the fuel cell. When people see an electrolyzer, they focus only on hydrogen production. But engineers know that every component is connected. The hydrogen value chain starts with an energy source. That energy is used to produce hydrogen. The hydrogen must then be purified. After purification, it is compressed. Once compressed, it is stored. Then it transported. Finally, it is used in a fuel cell, industrial process, or another applications. The challenge is that weakness at any point affect the entire systems. If, hydro- if hydrogen production is efficient but storage is poor, then overall system become insufficient. If storage is excellent but purification is not good, then fuel cell may fail. As engineers, we must always think in a system rather than individual components. Whenever you study a hydrogen technology, ask yourself, where does it sit in the value chain? What are the losses? What can fail? And what engineering discipline is responsible for solving that problem? The mindset will help you to understand every topic that follows. Now let's look at the two most important methods used to produce hydrogen. The first method is steam methane reforming, commonly known as SMR. The process reacts natural gas with a steam at high temperature, usually between 700 and 1000 degrees Celsius. The result is a hydrogen-rich gas mixture. SMR is a hydrogen production method because it is a mature, reliable, and relatively less expensive. However, it produces significant carbon dioxide emission. This is why hydrogen produced from conventional SMR is called a grey hydrogen. The second method is water electrolysis. Electrolysis uses electricity to split water molecules directly into the hydrogen and oxygen. If the electricity comes from the renewable sources such as solar or wind power, the resulting hydrogen is known as a green hydrogen. Electrolysis eliminates direct carbon emission during hydrogen production. However, it introduced new engineering challenges. Electrolyzers are very expensive. Renewable electricity, it varies time to time, and long-term stack durability remains an important issue. Throughout this course, we will study both technologies in details and understanding where each one makes sense. You may heard terms like green hydrogen, blue hydrogen, or a gray hydrogen. These colors are not scientific classification. They are simple, convenient way to describe how hydrogen is produced. Gray hydrogen is primarily from natural gas using steam methane reforming without carbon capture. It currently dominates global production but has high carbon emission. Blue hydrogen also uses fossil fuel, but carbon capture and storage technologies are added to reduce emission. The effectiveness of blue hydrogen depends heavily on how much carbon is captured and how much methane emissions are managed. Green hydrogen is produced by electrolysis powered by renewable electricity. It offers the lowest emission when the electricity source is genuinely renewable. Pink or purple hydrogen uses nuclear electricity or electrolysis. As an engineer, we should never evaluate hydrogen based on only color levels. We must evaluate the entire process, energy inputs, emission, and system boundaries. The color is the only starting point of the analysis. Only the beginning. The hydrogen leaving a production facility is rarely ready for a final use. Fuel cells are extremely sensitive to impurities. Even such as carbon monoxide or sulfur compounds can damage catalysts and reduce performance of the hydrogen fuel cell. Therefore, purification is a critical step in a hydrogen value chain. Technologies such as absorption, membrane separation, and palladium-based purification system are used to achieve very high purity levels. Once purified, hydrogen must be compressed for a practical transportation and storage. Hydrogen has extremely low volumetric energy density. In a simple terms, it takes up a lot of space. Compression helps solve this problem but introduce another challenge. Compression requires energy. This process also generates heat and places significant stress on equipments. Engineers must carefully balance production efficiency, purification requirements, transportation cost, and storage requirements at one of the most important engineering challenges in this entire hydrogen industry, that is storage. At a first glance, hydrogen appears to be an ideal fuel. Hydrogen contains approximately 120 megajoules of energy per kilogram, making it the highest energy content fuel by mass commonly available. Hydrogen contains approximately 120 megajoules of energy per kilogram, making it the highest energy content fuel by mass commonly available on Earth. This sounds amazing. However, there is a catch. While hydrogen has excellent energy density by weight, it has very poor energy density by volume. In a simple word, 1 kilogram of hydrogen contains a lot of energy, but it occupies a very large amount of space. This creates what engineers call the volumetric storage paradox. To solve this challenge, engineers use three major approaches. The first one, the first is a compressed hydrogen storage. In this method, hydrogen is stored in a high pressure tanks, commonly at 350 bar or 700 bar. This is the most common solution used in a fuel cell vehicle today. The second method is a liquid hydrogen storage. Hydrogen is cooled to approximately minus 253 degrees Celsius, where it becomes liquid. The dramatically increased storage density but requires cryogenic system that significant energy for liquefaction. The third method is a material-based storage. In this approach, hydrogen is chemically stored with another material such as a metal hydride or a liquid organic hydrogen carriers. They offer excellent safety and storage density but often add weight and complexity. Throughout hydrogen engineering, storage is often the deciding factor between a successful and unsuccessful application. Make hydrogen useful as an energy carrier, the fuel cell. A fuel cell is an electrochemical energy conversion device. Unlike an internal combustion engine, it does not burn fuel. Instead, it converts chemical energy directly into the electricity. Let's walk through the process step by step. Hydrogen enters the anode side of the fuel cell. At the anode, a catalyst separates the hydrogen molecules into protons and electrons. The protons travel through a special membrane called the proton exchange membrane, or we can call PEM. The electrons cannot pass through the membrane. Instead, they are focused to travel an external electrical circuit. This movement of electron creates a useful electrical power. At the cathode side, oxygen from the atmosphere combines with the incoming proton and electron. The final products are water and heat. This is why fuel cells are often described as a clean energy devices. The primary byproduct is water. An important point to remember is that fuel cells are not batteries. A battery stored energy internally. Fuel cell continuously produce electricity as long as hydrogen and oxygen are supplied. That is why fuel cells are often described a continuous power generator. Modern PEM fuel cell can achieve electrical efficiency exceeding 60%, significantly higher than many conventional combustion systems. Well, hear about hydrogen, they immediately think about the future technologies. However, hydrogen is already a massive industrial commodity. In fact, hydrogen is heavily used today in a petroleum refining and fertilizer production. Let's start with the refineries. Crude oil contains sulfur and heavy hydrocarbon compounds that must be removed or upgraded before fuel can be sold. Hydrogen plays a critical role in this process. Modern petroleum refining would not be function efficiently. Ammonia production. Ammonia is one of the most important chemicals in the world because it is used to manufacture fertilizers. The food production system that supports billions of people rely on ammonium-based fertilizer. Without hydrogen, ammonia production is impossible. This is why ammonia is often considered one of the first major market for green hydrogen. The infrastructure already exists, the demand already exists. The challenge is replacing carbon incentive hydrogen with a cleaner alternatives. For engineers, this means hydrogen is not just a future opportunity. It is already massive industry undergoing transformation towards the green hydrogen. Are relatively easy to electrify. Passenger car, home appliance, and consumer electronics are good examples. However, some sectors are much more difficult. These are often called hard to abate sector. One example is steel manufacturing. Traditional steel production relies heavily on a coal. Coal acts both as a fuel and as a chemical reducing agent. Significant carbon dioxide emission. Hydrogen offers an alternative. In direct reduced iron process, hydrogen can replace coal as the reducing agent. Instead of producing carbon dioxide, the reaction produces water vapor. This concept from the foundation of green steel manufacturing. Another important area is heavy transportation. Large trucks, buses, trains, forklifts, mining equipment, and port vehicles often require long operations hours and rapid refueling. Battery systems become increasingly heavy as energy requirement increases. Hydrogen fuel cells provide a potential solution. Refueling can take only a few minutes, vehicle range remains high, and payload capacity is preserved because hydrogen system can be lighter than large battery packs. This is why many experts believe hydrogen and batteries will coexist rather than they compete directly. Each technology solves different engineering problems. Slide 11. Application extend far beyond transportation. One rapidly growing area is stationary power generation. The data centers, hospitals, telecommunication tower, and critical infrastructure require a high reliable backup power system. Traditionally, diesel generators have been used for this purpose. However, fuel cells provide a cleaner alternative. They operate quietly, produce minimal local emission, and can provide reliable backup power during the grid outage. Hydrogen also enables long-duration energy storage. Renewable electricity generated during periods of excess production can be converted into the hydrogen and stored up in weeks or even months. When energy is needed, the hydrogen can be converted back to the electricity. The capability is extremely important because batteries are not always economical for long duration storage. Hydrogen is also becoming important in maritime and aviation sector. Directly, direct hydrogen use can be challenging because of for storage requirements. Instead of hydrogen is increasingly viewed as a building block for synthetic fuel such as the green ammonia, green methanol, and sustainable air fuel. These fuels can leverage existing transportation infrastructure while reducing the carbon emission. Slide 12. Safety becomes a major topic. As an engineer, we should approach safety with a facts rather than a fear. Hydrogen has been used industrial for more than a century. It is now a new technology. However, hydrogen possesses unique physical properties that require careful engineering. The first challenge is a leakage. Hydrogen molecules are extremely small and can escape through a tiny opening that would contain other gases. These require high quality fittings and leakage detection system. The second challenge is a pressure. Many hydrogen storage systems operate at 100 bar of pressures. This requires specialized pressure vessel, regulators, and pressure relief system. Another consideration is ignition. Hydrogen has a wide flammability and require relatively little energy to ignite. Engineers therefore use ignition system, gas detectors, grounding methods, strict safety procedures. Finally, hydrogen can cause metal degradation known as hydrogen embrittlement. Finally, can cause material degradation known as hydrogen embrittlement. Some some metal because weaker after prolonged hydrogen exposure. Some metal become weaker after prolonged hydrogen exposure. Engineer must carefully select material to ensure long-term reliability. Good hydrogen engineering is not about the eliminating risk. It is about the understanding risk and controlling it systematically. Slide. Technology alone does not create an industry. Large-scale deployment also require policy support, infrastructure investment, and long-term planning. This is where government initiative become an important. India's National Green Hydrogen Mission is one of the country's most ambitious clean energy program. Objective is to establish India as a global leader in a green hydrogen production, utilization, and export. The mission targets the development of millions of tons of annual green hydrogen production. The strategy includes investment in electrolyzer manufacturing, industrial decarbonization, hydrogen hubs, research programs, infrastructure development. For engineering students and professionals, this creates significant opportunities. New project requires engineers, new factories require engineers, new technology also requires engineers. The hydrogen transition is not simply an environmental initiative. It is also industrial and economical transformation. Understanding this policy drives the help engineer anticipate the future market demand and career opportunities. Slide 14. One of the most exciting aspects of hydrogen engineering is that it is create opportunities across multiple disciplines. This is not a field reserved only for the chemical engineers. Chemical and engineer work on reaction pathways, catalysts, purification, technologies, and plant integration. Mechanical engineers focus on a pressure vessel, thermal system, piping network, compressor, and metal performance. Materials engineers study catalyst development, membrane technology, corrosion, and hydrogen embrittlement. Electrical engineers contribute through power electronics, grid integration, electrolyzer systems, and fuel cell control system. Safety engineers perform risk assessment, leak detection, planning, compliance of other activities. Project engineers coordinate large scale of hydrogen infrastructure projects. No matter your engineering background, there is a place for you within the hydrogen value chain. As this industry grows, interdisciplinary collaboration will become one of the most valuable professional skills. Slide 15. Introductory module. I want to leave you with one important idea. Do you think of hydrogen as a magic fuel? Think of hydrogen as a powerful engineering tool. Hydrogen is not the solution to every energy problem, but is an excellent solution for specific challenges. Hydrogen can function as a low carbon chemical feedstock. It can provide long duration energy storage. It can support industrial decarbonization. It can enable cleaner transportation in applications where batteries face limitations. Most importantly, hydrogen only makes sense when we evaluate the entire value chains: production, purification, compression, storage, transportation, utilization, and safety. Throughout the rest of this course, we will explore each of these topics in depth. By the end, you will not only understand hydrogen technologies but also develop the engineering mindset required to evaluate them critically and professionally. Thank you for joining this journey, and let's move on to the next section of the hydrogen engineering masterclass.